All right, let's begin here. Before we get started, three quick announcements. Um, First is that Kent State has actually renewed the site license for Mathematica now. And so if any of you were holding off on trying it out until we got this taken care of, now would be a good time to try again with that. So I trust that Wolfram will now respond to the emails and will now send you emails with the necessary site license password. If they don't, I don't know, let me know, but I don't know what I'm going to do about it. But anyhow, we can try. Second, a reminder, homework number 3 is due today, so please send that to me if you have not done so already. For homework number 4, that one's not quite ready yet, but I will be posting that one on Monday, so hold off till then. Okay, so.
Cut off for the homework time. Do you accept that like till midnight today? Is that the deal?
Sure, fine.
Okay. It won't be that late. I just didn't know.
I haven't formalized it that much, but yes, fine, till midnight tonight. Okay. So I'm going to do one more example of solving Schrodinger's equation in a one-dimensional potential energy. Okay, and then I'll move on to the third chapter in the book. Okay. Before I get into the last example, I want to point out something that's kind of an analogy between classical mechanics and quantum mechanics. Okay. So what I want to point out is the distinction between bound and unbound states in classical or quantum mechanics. Okay. So let me remind you, in classical mechanics, we have the distinction between bound states versus, well, what we might call unbound states. That's not a real word. The physics word that people usually use is scattering states. And the basic idea here is that in a bound state, a particle is stuck somewhere. It's confined in a limited region. And in a scattering state, the particle can go off to infinity. Okay, so let's just write that. So particle is confined versus particle can go to infinity. And one nice way to think about this in classical mechanics is just to say, suppose we launch a spacecraft from Earth. Okay, so here's Earth. Right, and if we launch a spacecraft, the spacecraft might stay in orbit around Earth, or it might escape, depending on its initial velocity when it's launched. Okay? And so if it's launched with a moderate energy to start with, then it might go into a circular orbit like this. Or at higher energies, it might go into an elliptical orbit, something like that. But If we launch it with even more energy, then it will go into some other trajectory that doesn't come back to Earth. Okay? And so the higher energy trajectory could be something like this, which is a parabolic orbit. That's the borderline case, or even higher energy case would be a hyperbola. So a hyperbolic orbit. Okay, so here, I messed up my nice table with all this drawing. So let me try again. Okay, so in my table, I meant to say for the bound state versus a scattering state, the examples for orbital dynamics here would be a circular orbit or elliptical orbit, and here is parabolic or hyperbolic. Hyperbolic. Okay, so both of these things can happen in classical mechanics. And what makes the difference between these things is what's the energy of the particle. Okay, so in the case of a bound state, the particle energy is less than the energy needed to go to infinity. And for a scattering state, the particle energy is greater than or equal to the energy needed to go to infinity. Okay. So when we're thinking about a particle moving in gravity, we know that there is gravitational potential energy. Right? So there's some potential energy V of R as a function of R, right? Which is the negative G M over R, right? And so this is a potential energy that looks like that, okay? And so if the particle starts on the Earth, it has a negative potential energy, something like that, right? Where that's the radius of the Earth. Right? And then the particle, the rocket, right, also has some kinetic energy from when we launch it. Okay, and so then you could say the question is, what's the sum of the potential energy and the kinetic energy? Is it greater or less than the energy needed to go to infinity, which is just here, right? So if the sum of kinetic plus potential is less than the energy needed to go to infinity, then the spacecraft can't go to infinity, right? Then it stays confined near the Earth, right? And so it has to be in a circular orbit or an elliptical orbit. On the other hand, if the energy is greater or equal to the energy needed to go to infinity, then the spacecraft will go to infinity, right? And so it'll just fly away and never come back, right? And so you'll have an energy that's up here or there, or something like that, right? So that the particle can keep on going. Okay, so this is all in the classical mechanics, right? So in classical mechanics for orbits. Now, let's think about the three quantum mechanics problems that we have done so far with this terminology. So the bound state versus scattering state. Okay, so I'm going to do this for quantum mechanics. So the first problem that we talked about this semester was the particle in a 1D box. So that is a potential energy like this, right? Where there's a V of X as a function of X that goes up to infinity suddenly, right? As X goes to 0 or X goes to A. Okay? So in this case, the energy needed to go to infinity is infinity, right? The particle cannot possibly go to infinity, right? So if it has any finite energy, it must be bound, right? And so this should really be in the column of bound states. Ooh, I can move it. Whoops, wrong tool. Let's try again. Yeah, ooh, I can move it. Cool. Okay, so that goes in the column of bound states. Okay, so this is the example of a particle in a 1D box. Okay, now that was the first thing we did, right? And so the point is that it is always bound because it would take an infinite amount of energy to escape. Okay, now how about a harmonic oscillator? Okay, so that one has a potential energy for V of X that is a parabola like this, something like that. Okay, so in this case, how much energy does it take to go to infinity? Again, it takes an infinite amount of energy to go to infinity, right? This is a potential energy that goes up, and it just keeps on going up as X gets bigger and bigger in a positive direction, or as X gets bigger and bigger in a negative direction, either way. So if the energy of the particle is any finite number, it is bound, right? It can't possibly escape to infinity. All right, so that was the second example. For the third example, we did the free particle, okay? And so the free particle has a potential energy which is just always 0. V of X equals 0 everywhere. So the plot of that, V of X versus X, this is a very boring plot. It's just 0. Okay, so the energy that's needed to escape to infinity is 0. Okay, so that means that if the particle has any energy, 0 or bigger, then it can escape to infinity. Right? And so this is a case where the particle is never bound, right? It is always a scattering state. never a bound state. Right? Whereas in the other two previous examples, right, it's always a bound state. Okay, so you've seen two examples for systems where it's always a bound state, and you've seen one example of a system where it's always a scattering state. Okay? Now, you've noticed, you may have noticed something about the states in each of these examples, right? That in the two situations where we have bound states, we have discrete states. That is, you can count the states, right? The lowest, the second lowest, the third lowest, etc. Right? You can count the states on your fingers, right? Whereas in the case of scattering states, it's continuous states. That is, you can't count the states on your fingers, right? There's a whole number line of possible values of the k parameter, and k can be anywhere on this number line, right? And so that means that in the situations where there are discrete states, you have to sum over the states. And when it's continuous, you have to integrate over the states. All right, so those are the three examples that we've done so far. Okay, now for the fourth example, I want to show you a situation where you can have both, right? Both discrete states and continuous states, or perhaps I should say both bound states and scattering states, right? That you can have a single problem with both of these features. And it kind of makes sense that there should be a single problem with both of these features, because that's what we have in classical mechanics, right? In classical mechanics, we know that the gravitational potential energy can have both kinds of states, bound and scattering, right? That the same gravitational potential energy can have, circular and elliptical orbits, which are bound, and parabolic and hyperbolic orbits, which are unbound, they're scattering, right? So the same potential energy can do both of those things. And so stands to reason in quantum mechanics, maybe the same potential energy can do both of those things also. Okay. Now, let's suppose we want to design a potential energy that would have both of these features. Okay, so we could say, what would we want to build into the potential energy that could do both things? Okay, well, for sure, we want the potential energy to be not flat, right? If we want to have the possibility of a bound state, the potential energy can't be flat. It has to go down somewhere, right? In order to have something be bound, right? Otherwise, it can't possibly be bound. Okay, so the potential energy must go down somewhere. Whoops, like this feature. Okay, but on the other hand, when the distance goes to infinity, we really want the potential energy to be flat, right? Not something that just keeps on going up, right? Because if it keeps on going up, then for sure everything will be bound, right? The only way that you could possibly have a particle escape is if the potential energy becomes asymptotically flat, right? That going away from the center of the system, the potential energy has to be flat. Okay, so we could say, let's try to do both of those features. Okay, so I'm going to try to design a V of X to have both bound and scattering states. Okay, so I want to say, one necessary feature is it needs a potential well somewhere. And the other feature is it has to become flat as X goes to infinity. Okay, so let's work on that. Okay, so idea number one. Okay, for idea number one, let's maybe try the same kind of thing as the gravitational potential energy. Okay, so that would be a potential energy V of X as a function of X, which something like this, right? It would go way down at X goes to 0, but it's flat at infinity. And so a nice function for this would be V of X is some negative constant over X. Let's say absolute value of X. Okay. So it'll be symmetric between the two sides. Yes, this would certainly have those features. Okay, and a nice example of this is basically the hydrogen atom, where there is a Coulomb attraction between the proton and the electron, right? And so, if we want to make a model for the electron in a hydrogen atom, right, it feels a potential energy like this, which is attracting it towards the proton, right? And so it might be bound in an orbit around the proton, or maybe it can escape if it has a high enough energy, and then the atom would be ionized. Okay? This is a great example, and we will do this near the end of the semester when we are doing quantum mechanics in 3 dimensions. And it's kind of the killer app for quantum mechanics. And so it's a great problem, but it's too difficult for us to do yet. Okay, we have to postpone that one. Okay, so now let's say, try to make something simpler than that. Okay. So we could say for idea number 2, let's see if we could just make a potential energy that is flatter. Okay, so I'll make a potential energy like this. Okay, so it's flat, and then it goes down, and then it goes up, and then it's flat again. So this is something that I call the golf course potential in honor of President Trump, because it looks like, it has the putting green over here that's flat, and then there's a little hole for the golf ball. Okay, so the golf ball, it could be bound inside the hole, or it could be free to roll around on the putting green, okay? And so we could try to solve something like this, right? And for sure, it would be easier than the hydrogen atom, okay? Because it's flat in all these regions, okay? There is a real word for this, by the way. It is called the finite square law. And so that is discussed in the book also. Okay, so yeah, we could totally do this, okay? But I want something even easier than this, okay? And so to make something even easier than this, let's try idea number 3, okay? So for idea number 3, let's say we go with the golf course potential, but I'll make the hole extremely narrow and extremely deep. Right? So that is, I'm going to take the limit as the hole gets really narrow and really deep. Right? So it will be flat, and then it will go down and go back up right there, and then be flat again. Okay, so this is my v of x as a function of x. So the notion is that this is just like the golf course potential, but I'm going to take the limit as it's extremely narrow and extremely deep, okay, with the product of the width times the depth being constant. So this then is just like the Dirac delta function that we were talking about on Tuesday. Okay? This is the delta function potential. And it's an upside down delta function, right? It's a delta function multiplied by some negative number. Okay? So we could write it as v of x is negative constant times delta of x. And the constant, well, the book calls it alpha. So we'll call that also. Okay, so this then becomes the example that I want to try out, right? It's this limit of the golf course potential where the hole is extremely narrow and extremely deep, and it can be written as this Dirac delta function. Now, you guys are probably wondering, am I telling you that this delta function thing is easier to solve than this thing, which looks like it just has 3 nice flat regions? And the answer is yes, that's exactly what I'm telling you. That the delta function thing actually is easier to solve than this thing. And so yes, I'm going to show you how to solve it. And then after that, maybe I can give some hints about how you would solve the golf course thing, but that's in the book. Okay. Questions about this, the goal, right? So I've told you, I spent half an hour talking about the goal, but does the goal make sense to you guys? Okay. So let's try it. All right. Now, this is another example of working with the Dirac delta function, which I mentioned briefly and in the class on Tuesday, and asked you to maybe refresh your memory about if you might hypothetically have seen it in a math class. Okay, so let me quiz you about one thing that the Kent State Math Department may or may not have taught you. Let's, in physics, we often talk about units. Okay, so that's important. What are the units of delta of x? Okay. Does anyone want to take a guess about how that would go? The units of delta of x. Well, we know what x is, right? X is a length in this case, right? And so, x is some meters. Okay? So if we want to know the units of anything, we want to put it into an equation. And then we know the units have to match on both sides of the equation. So the fundamental equation for delta of x has to be an integral, right? And so we started off by saying that we have the integral of delta of x dx is equal to 1. Okay, so when you integrate something dx, that has the same units as x, right? And so it has units of length. Okay. On this side of the equation, 1 is dimensionless. Okay. So we must have that delta of x has units of 1 over length. This is always true for a delta function, right? That the units of the delta function are 1 over the units of whatever goes inside the delta function, right? And so if you had delta of E, where E is an energy, then we would need to say the integral of delta of E dE is equal to 1, right? And so this is units of energy. This is units of 1 over energy. So it's not enough to say that the delta function goes to infinity, right? But it's infinity in some units. Okay, and the output units of the delta function are 1 over whatever the input units of the delta function are. Okay, so that means if we have the potential energy, V of x is minus alpha delta of x. V of x is an energy. Delta of x, that has units of 1 over length. So that tells us that alpha has to have units of energy times length. Okay. And so, with whatever equations we derive in the end, we should be able to check the units, right? And see wherever alpha goes, we should be able to plug in that it's an energy times a length and make sure that that gives us the right units for whatever we get. Okay, so let's see if we can solve the potential energy, solve the Schrodinger equation with this potential energy function. Okay, so we want to solve the Schrodinger equation. Okay, which is, of course, as always, IH bar d psi dt is minus h bar squared over 2m. It's the second derivative of psi with respect to x. And then minus alpha delta of x psi of x and t. Okay, so the beginning of this solution is the same as always, right? That is, we do separation of variables. So we assume that this time-dependent wave function is some time-independent wave function times a time-dependent factor. And we know what the time-dependent factor is. It has to be exponential of minus I energy t over h bar, right? We proved that in general. Okay, and then this lowercase psi has to satisfy the time independent Schrodinger equation, which is that the Hamiltonian acting on psi, that is minus h bar squared over 2m second derivative of psi with respect to x minus alpha delta of x psi of x is equal to E times psi of x. Okay, so this then is the differential equation that we want to solve to get out the wave function in the delta function potential. Now, you're looking at this and you say, how do we solve a differential equation which has this delta function right in the middle of it, right? It means that there is some place where this thing goes to infinity. And how do we put that into a differential equation solution? Okay, so the trick for doing that is that we want to solve in two separate regions, okay? So to solve for x negative and x positive, for sure we can do that because we know that the delta function is 0 in those places, okay? And then connect the solutions in a way that is consistent with the delta function, as I will show you. Okay, so let's first just think about how to solve it in the two domains of x negative and x positive. Okay, so in those two domains, we could say for x negative, we have the delta function is 0. So it's just h bar squared over 2m, the second derivative of psi with respect to x is equal to E psi. And for x is positive, it's just the same thing. So, for these things, it looks just like the free particle. Okay. Except for one little distinction, which is that E might be positive or negative. For the free particle, we know there's no potential energy, so the energy is just kinetic energy. Kinetic energy is positive, right? But in this case, the energy is a combination of kinetic and potential energy. The potential energy is not zero for the whole state. The potential energy is zero. The potential energy is zero at these positions, but the expectation value of the potential energy that involves everywhere, not just a single position, but it's everywhere, right? Like when we had the harmonic oscillator, for example, right? We could calculate the average kinetic energy and the average potential energy in some state, okay? And the average potential energy in some state doesn't depend on what's the harmonic oscillator potential at a particular X, but the states are spread out in X. And so it's some average of a whole spread out potential energy. Right? So it's the same thing here, right? We have a potential energy that's all spread out. We have a potential energy that looks like this thing, right? And so if the wave function is going to be something spread out, that'll know about what's the potential energy here in the delta function well. Okay? And so there could be a negative potential energy and a positive kinetic energy. And the sum of those things, it might be positive, it might be negative. We don't know that in advance. And really, that's what we're trying to figure out when we figure out, is it a bound state or a scattering state, right? Remember, the bound state means the energy that's needed to go to infinity, okay? And the energy that's needed to go to infinity in this potential is zero, right? So if the energy is less than zero, that means the particle is bound, right? If the energy is greater than zero, it means the particle can escape. So it's a bound state versus a scattering state. You all right with this point? I'm seeing some skeptical looks, maybe. Any questions about this point? No? All right. Okay. So we don't know whether the energy here is going to be positive or negative. They are both possibilities. And so if we want to make sure we get all the solutions, we better try both possibilities. Okay, so we're going to try both E negative and E positive. So let's say case one is E negative. Let's try that, okay? So E is negative. So to help me remember that it's negative, I'm going to write it as negative absolute value of the energy, okay? So that means that the Schrodinger equation, the time-independent Schrodinger equation, is negative h bar squared over 2m. This second derivative is negative absolute value of energy times psi. Okay, so that then tells us that the second derivative of psi is a positive number, 2m absolute value of E over h bar squared times psi. Okay. So, this is, in this case, it's different from the free particle, right? Because the free particle had a second derivative that was a negative number of psi. Now, we can totally solve this, right? A second derivative is equal to a positive number times the function itself. Let's call this positive number kappa squared. Okay, so this is my handwriting for the lowercase Greek letter kappa. Okay? My handwriting's not so good on that, but just to let you know. Okay, so that's my handwriting for kappa. Okay, so the equation is that the second derivative is equal to kappa squared times psi. So the solutions for that are just exponentials, right? And so not complex exponentials, but just ordinary exponentials. Okay, so the solutions are e to the kappa x and e to the minus kappa x, right? Either of those solutions has the second derivative equal to kappa squared times the function itself, right? So our solution has to be one coefficient times the first thing plus one coefficient times the second thing. Now, we need to do this solution for x negative and x positive, right? That's our two places where we're solving it. Okay? In both of those places, we have these solutions with coefficients, but the coefficients might be different when x is negative and x is positive. Okay, so we could say our solutions are for x negative, we have a psi of x is one thing, a times e to the minus kappa x, plus another coefficient, b times e to the kappa x. Right? And for x positive, it's the same kind of functions, but there might be different coefficients in front of them. So I'm going to copy from the book, and the book uses the letters F for e to the minus kappa x plus g e to the kappa x. Okay, so these are the most general solutions of the time-independent Schrodinger equation for negative x and positive x. Now, these general solutions, they have these four unknown coefficients, a, b, f, and g. Now, if we want to get information about these coefficients, we have to go to the boundary conditions, right? And so you know we've done that in lots of problems, right? So for example, for the particle in a box, right? When we go to the boundary conditions, that told us about whether you can have sine or cosine solutions, right? So let's go to the boundary conditions. Okay. So for one thing, we know that the function has to be normalizable, okay? So the function has to be something that you can integrate from minus infinity to infinity, right? And so we know we need that psi goes to 0 as x goes to plus or minus infinity. That's the only way it can possibly be normalizable. Okay. So let's check what happens as x goes to negative infinity. Let's see, if x is negative infinity, we better use the negative x solution. Okay, so we know we're going to have a combination of the a term and the b term. Okay. Now, when x goes to negative infinity, if I put negative infinity into the b term, we get negative infinity times kappa, some positive number. The product is 0. No problem. But if I put x is negative infinity here in the a term, we have negative infinity times negative kappa. That's the exponential of positive infinity. Okay? That's a huge number. Well, we can't have that, right? The function would certainly go crazy then when x goes to minus infinity. It would violate this boundary condition hugely. So for that reason, we better have a equals 0. Okay, now what? Now, what about as x goes to positive infinity? So if x goes to positive infinity, we better use the solution for positive x here. Okay, so we can put x's positive infinity into this negative exponential. We have the exponential of negative kappa times infinity. Okay, exponential of negative infinity, that's 0, no problem. But if we put x is positive infinity in here, we have the exponential of positive infinity. That goes to infinity, right? It's a huge number. That would certainly violate the boundary condition. So we better have g equals 0 so that we don't have that problem. Okay, so now we have partially simplified the problem, okay? So now we know that for x is negative, the solution has to be psi of x is b e to the kappa x. And for x positive, we have psi of x is f e to the negative kappa x. Okay, so now we're down to having two coefficients that we don't know, right? The b and the f. Right? So the question is, how are b and f related to each other? Well, if we want to answer that, we need to use something about what's happening at x equals 0. Right? So we know if I make a plot of psi of x versus x, okay, for x negative, we have some decreasing exponential like that, okay? And it goes up to the number b right there. Okay? For x positive, the function is a decreasing exponential like that, right? Which goes up to the number f, okay? But the point is that psi must be continuous at x equals 0. Okay, you can't just have a jump in psi like this. Okay, why not? Well, because Schrodinger's equation involves the derivative of psi. In fact, it involves the second derivative of psi. And the only way that that's even meaningful is if psi is a continuous function everywhere. Okay? And so for that reason, we must have b equals f. So that means I could erase this. And the right way to draw it would be a function that looks like this. Okay, so that it's symmetrical between the two sides. Okay? And so in that case, we could write it on both sides as psi of x equals b times the exponential of minus kappa absolute value of x. Right? And so you can see that this thing, if x is positive, it turns into this, right, with b equals f. If x is negative, it turns into that. Okay, so we're making pretty good progress. We have this form for the wave function on both sides of x equals 0. Okay? But you'll notice that we still haven't used the delta function, right? I said that we're solving this delta function potential, but I still haven't done anything with the delta function. Okay, so now that we have this much of the solution, let's go back to the Schrodinger equation that actually has a delta function in it. So now we'll go back to the time independent Schrodinger equation. Okay. And that says minus h bar squared over 2m, this second derivative of psi with respect to x, minus alpha delta of x psi of x is equal to e psi of x. Okay, and now I want to take both sides of this and integrate. So on both sides of this, I want to integrate dx. Okay. And this time, not integrate all the way from minus infinity to infinity, but I want to integrate just from a tiny little positive number, no, a tiny little negative number to a tiny little positive number. Okay, so I'm going to integrate from x equals 0 minus epsilon to 0 plus epsilon on both sides. On both sides of this equation. Okay, so integrate from just on one side of the delta function to just on the other side of the delta function. This is often a good trick for working with delta functions. Okay, so suppose we do that, okay? Now we want to do this integration term by term. Okay, let's start with integrating the second derivative term. Okay, so I want to integrate this term right there from x equals a tiny little negative number to a tiny little positive number. If I do that integral, it's the integral of the second derivative. Well, we know what the integral of a second derivative is, right? It's the first derivative, right? Because integration is the opposite of differentiation. Okay, so the integral of the second derivative of psi is minus, well, we have this coefficient, h bar squared over 2m, and then the first derivative of psi. So d psi dx, and I'm going to evaluate this from 0 minus epsilon to 0 plus epsilon. Okay, that is the integral of the first term. Okay, then the second thing is going to be a minus alpha integral from 0 minus epsilon to 0 plus epsilon delta of x psi of x dx. Okay. Now, I told you before that the integral of delta of x times any old function of x integrated from minus infinity to infinity is the any old function of x evaluated at 0. Okay, that still works here. Now, you may be thinking, what about these limits? These aren't the right limits. Right? This is just a little negative to a little positive. Okay? The point is, it doesn't matter because delta of x is 0 all the way from negative infinity to negative epsilon. And so I can take this limit to be negative infinity. Likewise, delta of x is 0 all the way from positive epsilon up to positive infinity. So this limit might as well be positive infinity. And then this whole term turns into the negative alpha times psi of 0. Okay, that's the integral of this term. Okay, the integral of the first term, I didn't write it out, but I could. It's minus h bar squared over 2m. And then d psi dx at 0 plus epsilon minus d psi dx at 0 minus epsilon. Okay. Now, how about on the other side of the equation? Okay. On the other side of the equation, we have e times the integral of psi of x dx from a tiny little negative number to a tiny little positive number. We don't know what the integral of psi is, but whatever it is, the integral gets smaller and smaller as epsilon gets smaller and smaller, right? If we have a function like this for psi, and we are integrating it just from negative epsilon to positive epsilon, the integral is the area in there. And if epsilon is an extremely small number, this integral gets arbitrarily small. Okay? And so in the limit of small epsilon, that integral is just 0. Okay. So this equation then gives us some information that relates the derivatives of psi to psi itself. Okay, so now let's see how that's related to the parameters in this equation, the b and kappa in that equation. Okay. Well, for psi of 0, here, I'll write it out, right? So psi of x is b times this exponential of absolute value of x, right? And so it is b e to the minus kappa x for x positive, b e to the kappa x for x negative. Okay, so psi of 0, if we plug in x equals 0 in either of these limits, we just get b. So psi of 0 is b. Okay, what about the derivatives? D psi dx, I need to differentiate in each of these two cases separately. So it is negative kappa b e to the minus kappa x for x positive, and it is kappa b e to the kappa x for x negative. Okay. So if I plug in a tiny little positive number, Okay. If it's a positive number, I have to use the first line. And if the number is really tiny, then I put in x equals 0 there, and I just get negative kappa b. Likewise, d psi dx for a tiny negative number for x, that if x is negative, I have to use the negative x line. So I put in x is a tiny negative number. I'll put in x equals 0 right there. It's 1. So the derivative is positive kappa b. So this shows us that the first derivative of psi is discontinuous at x equals 0. But we knew that already from our plot, right? The first derivative is something positive on the left side and something negative on the right side, okay? So right at x equals 0, there's a discontinuity from a positive derivative to a negative derivative. Okay, so let's put those numbers into this equation right here. Okay, so that then says that negative h bar squared over 2m. Okay, so I want the derivative at positive epsilon minus the derivative at negative epsilon. Okay, so that's negative kappa b minus kappa b. So all of that minus alpha times psi of 0, that's b, equals 0. Okay, so negative h bar squared over 2m times negative 2 kappa b has to be equal to alpha b. So h bar squared kappa b over m equals alpha b. The b's cancel. And so what this equation does is it tells us the number kappa, right? We know the mass. I mean, that's the input information. Mass is input information. Alpha, the strength of the potential, is input information. H bar is for sure input information. Okay. So it tells us kappa for our bound state. So it tells us that there is a bound state, okay, with a specific value of kappa, right? And the equation for this state is psi of x is e to the minus kappa absolute value of x. The plot of this looks like this. Psi of x as a function of x down, starts at b, and it decreases exponentially as we go away from the origin, right? And so if we go out a distance of 1 over kappa or negative 1 over kappa, then we are the function is down by a factor of 1 over e compared to where it starts. All right? So this means that the particle is confined to a distance of about 1 over kappa from the origin. So, if we think about this like a game of golf, right, it means the golf ball isn't exactly stuck in the hole, but it's stuck near the hole, right? The hole is zero width, right? It's infinitely deep and zero width. And the golf ball, it can move a little bit onto the green, but not too far, right? It's stuck a particular distance away from the center of the hole. And this is a state which has an energy which we defined a long time ago, right? Because kappa is related to the energy. Somewhere, way back here, kappa is related to the energy, right? So the energy is negative h bar squared kappa squared over 2m. And so that is negative h bar squared over 2m. And then let's see, kappa squared is m squared, alpha squared, h bar to the 4th. So negative m alpha squared over 2 h bar squared. Okay, so that's the energy of this state. So you see, we started saying, let's find the bound states. And we found exactly one bound state, okay? We found a bound state with this wave function and this energy. That's the bound state. Okay, so this was meant to be a problem that could have both bound states and scattering states. And in fact, we have found exactly one bound state. We have not yet looked for scattering states, right? Because a scattering state would be a state with energy positive. And here we said, let's consider energy negative. Right? So finding the scattering states is going to be another whole calculation for case 2, assuming that E is positive. So that we'll have to wait until Monday. Okay. I am going to stop here and I'll be glad to answer questions about this stuff. You might also want to look at the book's presentation of this stuff. And in any case, have a good weekend, you guys, as you ponder the quantum game of golf. And I'll see you guys on Monday.